Welcome students, welcome back. In the last lecture on this series of lectures on matrices, we saw what are known as elementary row operations and we saw how to use it to obtain what is known as the row reduced echelon matrix. In fact, in the towards the end of the last lecture, we saw an example. Now let us do one more example. Let the matrix A equal to 0 0 0 3 0 1 0 0 4 1 0 0 0 0 0 4 2 0. This is the matrix that we have. First thing that you will have to notice is that we have a 0 row. So, let us push it to the last one. R3 is swapped with R4. What we will have is 0 3 0 1 0 0 4 1 0 4 2 0 0 0 0 0. We have this. Look for the first non-zero row, which is the first one, and the first non-zero element is this 3. So, let us try to convert it into 1. R1 is replaced by 1 by 3 times R1. What we will have is 0 1 by 3 0 1 0 1 by 3. Other rows remains unchanged. Now, let us convert the other element which is in that same column, which is 4 into 0. R3 is replaced by R3 minus 4 times R1. First row remains unchanged, 0 1 0 1 by 3. Second row again remains unchanged, 0 0 4 1. Third row we are making a change, 0 minus 4 times 0, which is 0, 4 minus 4 times 1, which is 0, again 2 minus 4 times 0, which is 2, 0 minus 4 times 1 by 3, you have minus 4 by 3. The last row remains unchanged, and then the next one is, let us look at this submatrix, this part. So, the first one is non-zero row is this and the non-zero element is 4. So, let us convert it into 1. R2 is replaced by 1 by 4 times R2, 0 1 0 1 by 3, 0 0 1 1 by 4, 0 0 2 minus 4 by 3, 0 0 0 0. Now, you have a 2 here. So, let us try to convert this 2 into 0. R3 is replaced by R3 minus 2 times R2, 0 1 0 1 by 3, 0 0 1 1 by 4, 0 0 2 minus 2 times 1, which is again 0, R3 minus 4 by 3 minus 2 times R2, which is half, 0 0 0 0. And so, the resulting matrix here is 0 1 0 1 by 3, 0 0 1 1 by 4, 0 0 0. So, minus 4 by 3 minus half, which is minus 11 by 6 Finally, you have, so you will have to consider this part. You have a non-zero, first non-zero element is this 11 by 6, we will convert minus 11 by 6, we will convert this into 1, R 3 is replaced by minus 6 by 11 times R 3, 0, 1, 0, 1 by 3, 0, 0, 1, 1 by 4, 0, 0, 0, 1, the remaining things are going to be zeros. And then now I have 1 by 4 and 1 by 3 here, I will have to convert them into zeros. R 1 is replaced by R 1 minus 1 by 3 times R 3, and similarly R 2 is replaced by R 2 minus 1 by 4 times R 3. 0, 1, 0, all three things remains unchanged. Only thing is that, so 1 by 3 minus 1 by 3 times 1, which is 0. Similarly, the next one 0, 0, 1, 1 by 4, 0, 0, 0, 1, sorry, this is 0, this is not 1 by 4, you have 0, 0, 0, 0. So, this is the, thus the row reduced echelon matrix of A obtained by applying the row elementary operations is the following matrix 0 1 0 0 0 0 1 0 0 0 0 1 and the last row is 0 0 0 0. Now, let us do one more example. Let the matrix A be 1 minus 2 3 minus 4 2 5. Let us try to convert this into its RRE. So, the first row is non-zero and the first element, the non-zero element is 1. So, let us not bother. So, what we will have to do is convert this minus 4 into 0. So, we will replace R 2 by R 2 plus 4 times R 1. So, the first row remains unchanged 1 minus 2 3, second row minus 4 plus 4 times R 1. So, minus 4 plus 4 times 1 which is 0, 2 plus 4 times minus 2. So, what you will have here is minus 6, last one 5 plus 4 times 3 which means 5 plus 12. So, you will end up with 17. Now, let us look at the next row. So, next to non-zero 1 is this minus 6 17 which is 1 by 2 matrix. So, we will have to convert this minus 6 into 1. R 2 is replaced by minus 1 by 6 times R 2. The first row remains unchanged 1 minus 2 3 0 1 minus 17 by 6. Our next aim here is we have this minus 2 which we will have to convert this into 0. So, let us do this. So, what will I do? I will replace R 1 by R 2, sorry R 1 plus 2 times R 2. I will have 1 0 in the next here, I want 0 here and I will have my 1 R 1 plus 2 times R 2 which means 3 minus 17 by 3 and I will have minus 17 by 6. So, what is 3 minus 17 by 3, which is 9 minus 17 by 3. So, 9 minus 17 you will have 8. So, minus 8. So, this will end up with 1 0 minus 8 by 3 0 1 minus 17 by 6. This is the matrix, that final echelon, row reduced echelon matrix. Fine. Having said about how to compute the row reduced echelon matrix, let us try to find out some of its applications or look at some of its applications. Wait. The first application that we will have is in finding what is known as rank of a matrix. How does one define the rank of a matrix? So, the rank of a matrix is defined as the number of non-zero rows in its row reduced echelon matrix. You reduce the given matrix into a row reduced to echelon matrix, look at the number of non-zero rows, and that is the rank of the matrix. Now, the question is, given a matrix A, how many row reduced echelon matrices are possible? If it is unique, then this rank makes sense, then the definition that we have given makes sense. If it is not unique, then what to do? If you are going to have 2, then which one should I consider? All these problems occurs. In fact, so let me just make a note, and I will not go into the details of this. Of course, this note will be intuitively clear why it is true. So, let me just remark or make a note saying that given a matrix A, then the row reduced echelon matrix associated with A is unique, which means given a matrix A, there is only one row reduced echelon matrix associated with this, that is the procedure that we have given just few minutes back, right, that gives you the unique row reduced matrix or the row reduced echelon matrix associated with this matrix A, and thus the definition of the rank of a matrix makes sense. Now, let us proceed to calculating the rank of the matrix. Well, let us look at the both the examples that we saw. The first example that we had just few minutes before. So, let us just look at the examples. The first one that we had is 0 0 4 1 0 3 0 1 0 0 0 0 0 4 2 0. This was the matrix that we had, and the row reduced RRE, right, we will just call it as RRE, right. This is the matrix that we have, and the RRE corresponding to this is 0 1 0 0 0 0 1 0 0 0 0 1 and 0 0 0 0. This was the matrix that we had. So, the number of non-zero rows in the RRE row reduced echelon matrix of A is 3. Therefore, rank of the matrix A is just 3. Let us look at the next example that we had. Second example, our matrix was this 1 minus 2 3 minus 4 2 and 5. This was the matrix that we had, and the RRE or the row reduced echelon matrix corresponding to this was 1 0 minus 8 by 3 0 1 and minus 17 by 6. This was the RRE that we had. So, the number of non-zero rows in this RRE is 2. Therefore, rank of A is. Now, let us do one more example. Let us choose A as 2 3 4 5 2 1. This is the matrix that we have. Now, let us try to convert this into its RRE. If you look at this matrix, there are no 0 rows. So, let us not bother about it. First, let us look at the non-zero first non-zero column. First non-zero column is the first column itself, and the first non-zero element in that first column is the first element which appeared in the first row itself, and which is 2. Now, let us make this into 1. So, we are going to replace R1 by half of R1. So, let me write it here. R1 is replaced by half of R1. You have 1 3 by 2 4 5 2 1. Next thing that you will have to do is you will have to convert this 4 and 2 into 0. So, I will have to replace R2 by R2 plus minus 4 times R1 and R3 by R3 plus minus 2 times R1. I have 1 and 3 by 2. I will have to convert these two into 0, right. Therefore, these two operations are done. So, now let us calculate the remaining 5 plus minus 4 into 3 by 2. So, minus 4 into 3 by 2, which is minus 6. So, 5 minus 6, it is minus 1. The next one 1 plus minus 2 into 3 by 2. So, minus 2 into 3 by 2, which is minus 3. So, 1 minus 3, which is minus 2, right. So, let me delete the first row and the first column. What I will end up with is this submatrix 2 by 1 submatrix, which is itself a non-zero, there is no non-zero row, and there is no, and you do not have the first non-zero element appears in the first one. So, let me first make that into 1. R2 is replaced by R2 is replaced by minus 1 into R2. 1 3 by 2 0 1 0 minus 2. I have this. Then I will have to make the other two elements into 0. I will replace R1 by R1 plus minus 3 by 2 times into R2 and similarly R3 is replaced by R3 plus 2 times R2, right. So, these two are going to remain unchanged and I will have 0 1 0. This is the echelon form that I have, and the number of non-zero elements, non-zero rows in this RRE row reduced echelon matrix is 2. Therefore, rank of the given matrix A is 2. Let us do one more example. Maybe the fourth example. One, 2, 0, 0, 0, 0, 0, 0, 0, 0, 1, 3. This is the matrix that I have. So, you have a 3 by 4 matrix. Let us try to calculate the rank of this matrix. You have a 0 row, which is the second row, which is above a non-zero row. So, let us push it to the last one, is swapped with R3. So, what will I have? 1 2 0 0, 0 1 3, 0 0 0 0. The first non-zero column is this. You have the first non-zero column, and the first non-zero element is itself 1. So, I am not bothered about this, and it is also 1. So, I am not bothered, and the other elements in that column are also 0. So, only thing that I will have to do is look at the other things. Let me delete the remaining one and let me look at the remaining submatrix, which is a 2 by 3 matrix. And now, the first non-zero column appears here, which is 1 and 0, and again if you look at this one 1 and 0, this 1 and 0, what is happening here? 1 and 0. This one, this 1 and 0, this is the first non-zero column, and the first entry is itself 1, and the other entries in that column or other entries in that column are 0. So, let me remove the first and second, first column and first row, and the remaining one is just the 0. So, I have finally, just by swapping, I have ended up with a row reduced echelon matrix. So, this is the row reduced echelon matrix obtained from the given matrix. The number of non-zero rows in this matrix, in this RRE, is 2. Therefore, rank of the matrix is, having said about the rank, the next application that we are going to look at is what is known as invertibility of a matrix. So, a square matrix A is said to be invertible if there exists again a square matrix B with order of B equal to order of A, such that AB equal to BA equal to the identity matrix, right. If you just multiply A with B or B with A, it should give you the identity matrix of the same order. Then if you can obtain such a matrix B, then you say that the matrix A is invertible. Now, how to verify whether a matrix is invertible or not, and this can be done by using what are known as the row elementary operations. So, how to obtain this? In fact, so let me just state a result. Suppose R is the RRE matrix, row reduced echelon matrix, obtained from the given matrix A, given square matrix, let me say this, then A is invertible if and only if the RRE matrix R is the identity matrix. How to check whether a matrix is invertible or not? Just find out its RRE. Once you know that the RRE that you have finally obtained is just the identity, then such a matrix have to be invertible. The matrix B is called as the inverse of A. The question is this: is the inverse of a matrix unique? Is the inverse of a matrix unique? In fact, the answer is yes. And how to prove it? Suppose that A is an invertible matrix. Let B and C be their inverses. That is, so AB equal to I equal to BA and AC equal to I equal to C. So, let me call the first one as 1 and the second one as 2. Now, let us observe a simple thing. Given any square matrix, A times I is going to be just A. Why is it so? Let us prove it. Let A equal to Aij and I, let me write it as let me write it as Bij, and what are these Bij's? Bij is going to be 1 if I equal to j, 0 if I not equal to j. This is what you have. So, now let us multiply A and I. So, A times I is going to be Aij times Bij, which by the definition of matrix multiplication, summation k running from 1 to n. So, let us assume that the matrix A is an n by n matrix. So, you have k running from 1 to n, Aik Bkj. Now, Bkj's, these are the entries of the identity matrix and therefore, this is 1 only if k and j are one and the same. So, unless my k is equal to j, right, this is going to be 0. So, the only term that survives is Bjj, while the all other terms are going to become 0. So, what I will have is just Aij Bj, right, and Bjj is 1. So, I will just end up with Aij, this is just the matrix A. And similarly, what will I have? So, let me just write down therefore, Ai is just A. Let me just mark it as 3. Similarly, I times A is also A, we call it as 4. Therefore, let me start with B, B equal to B times I this is from 3, but I is B times AC, right, this follows from 2, which is same as BA times C by associativity of matrix multiplication First one that we used is the equation 3, second one that we used is equation 2, and finally what we have used is the associativity of matrix multiplication, but from the equation 1 what will I have? I will have BA is just I times C, but I times C is C, this follows from I times C is C, this follows from equation 4. Thus, B equal to C. What we have shown is that the inverse of a matrix, if at all it exists, then it is going to be unique. Let us verify one more property for the inverse. For any two square matrices, A and B of same order, the invertibility of A and B implies the invertibility of AB, and the inverse of AB is equal to B inverse A inverse, right. So, the unique inverse that we obtained. So, once you know that a matrix A is invertible, right, then you know that the inverse is unique, then we will denote that inverse by A power minus 1, that is what we have. The inverse of AB power is my AB power minus 1, right, and it is given by B inverse A inverse. Now, let us go with the proof of this. How to verify that something is the inverse? So, the inverse of AB is B inverse A inverse. Well, let us verify that AB times B inverse A inverse is the identity, and similarly B inverse A inverse times AB is identity, and by the uniqueness this should be the identity for AB, sorry, this should be the inverse for AB. AB times B inverse A inverse, which is equal to A times BB inverse times A inverse, but BB inverse is just the identity. So, this is same as A times identity times A inverse, but A times identity is just A times A inverse, which is going to be identity. Similarly, B inverse A inverse times AB, which is equal to B inverse A inverse A times B, and A inverse A is the identity. So, I will have B inverse times I times B, but I times B is just B. So, this is same as B inverse B, which is going to be identity. So, the inverse of AB is, which is AB whole inverse, which is given by B inverse A inverse. Now, having said all these, let us now compute the inverse of a matrix using the row elementary operations. Before that, so let us just see how to compute it. What we observed is the following. What is that we observed? Suppose that you have a matrix A which is invertible, then the row reduced echelon matrix associated with that matrix A is the identity matrix. So, few observations. What is that? So, if rho is an elementary row operation, on the set of all matrices, then rho is invertible as a function. That is, rho is both 1 1 and 1 2, right, which means that you get another function g such that rho times g is equal to g times rho, which is equal to identity on the space of matrices. In fact, the last set of lectures on sets and functions, we observed that if you have a function which is 1 1 and onto, then such a function can be inverted. So, so the same thing is happening here, that is every row elementary operation can actually be inverted. So, if you observe the first row elementary operation, which is the interchanging of two rows, that is an invertible operation because its inverse is again interchanging the same set of rows. The second one, multiplying a given row, say ith row by a scalar alpha, the scalar lambda or alpha, then the inverse operation is multiplying the same ith row by the scalar 1 upon of that scalar, say lambda or alpha, right. Similarly, the third operation, the ith row is replaced by the ith row plus a scalar times scalar lambda times the jth row, right. Now, that is again invertible. So, if rho 1, rho 2, etc., rho m are the elementary operations performed on a matrix, on an invertible matrix, or the elementary operations performed on an invertible matrix A to obtain the identity matrix rather than starting with if, suppose, or the elementary row operations performed on an invertible matrix A to obtain the identity matrix. Then what do we have? Row 1 composed with, well, I will write it as row m minus 1, row 1, and if it is performed on A, what you get is the identity matrix. So, thus row m composed with row m minus 1 up to row 2 composed with row 1. When you apply this on the identity and multiply it with the matrix A, what you obtain is the identity matrix. So, this will imply that the inverse of the matrix A is row m composed with row m minus 1, row 1 applied on identity is the inverse. So, how to obtain the inverse of a matrix? Just apply the same set of elementary operations that you applied on A to obtain the identity matrix. Apply the same set of operations on identity, what you will end up with is the inverse of A. Now, let us do an example. A equal to 1 1 1 1 2 1 1 2 3. This is the matrix that we have. So, let us try to find the inverse of this. So, what we will have to do is write down the matrix A and along with this let us write down the identity matrix. Now, let us try to convert this part, the portion that corresponds to A, into the identity matrix, simultaneously applying the same operations on the identity matrix. So, once you know that this part has converted into identity matrix, we know that it is invertible, and then the one that you have obtained on the other end is the inverse of it, and the final row echelon matrix that we have obtained, if it is not the identity matrix, then we can conclude that the matrix is not invertible. Well, let us try to convert this into the row reduced echelon matrix into its RRE. So, you have the first non-zero row is the first one and the first non-zero element is 1. So, let us not bother, let us look for the other ones. The other ones we have 1 and 1. So, let us convert them into zeros, R2 minus R1 and R3 minus R1. First row remains unchanged. Second row R2 minus R1, 1 minus 1 which is 0, 2 minus 1 which is 1, 1 minus 1 which is 0, 0 minus 1 minus 1, 1 minus 1 1, 0 minus 0 0. Again R3 minus R1, 1 minus 1 which is 0, 2 minus 1 which is 1, 3 minus 1 which is 2, 0 minus 1 minus 1, 0 minus 0 0, 1 minus 0 which is 1. Now, let us look at the next non-zero row which is the second one, and now let us try to look at this one. You have 0 1 0. So, what we will rather do is, so we will have to convert this into 1 which is already 1. So, let us not bother, let us try to convert this 1 and 1 into zeros. R1 is replaced by R1 minus R2, R3 is replaced by R3 minus R2, R1 minus R2, 1 minus 0 which is 1, 1 minus 1 which is 0, 1 minus 0 which is 1, the other part 1 minus 1 which is 2, 0 minus 1 which is minus 1, 0 minus 0 which is 0. Second row remains unchanged, 0 1 0, minus 1 1 0. Third one R3 minus R2, 0 minus 0 which is 0, 1 minus 1 which is 0, 2 minus 0 which is 2, minus 1 minus minus 1 which is 0, 0 minus 1 which is minus 1, 1 minus 0 which is 1. Finally, you have 2, let us convert this 2 into 1, R 3 is replaced by half of R 3, 1 0 1, 2 minus 1 0, 0 1 0, minus 1 1 0, 0 0 1, 0 minus 1 1, sorry 0 minus half and half. So, what you will have is, now we will have to convert this 1 into 0, R 1 is replaced by R 1 minus R 3, 1 0 0, R 1 minus R 3, 2 minus 0 which is 2, minus 1 minus minus half. So, which is minus 1 plus half. So, you have minus half, 0 minus a half, you again have minus half. The other things remains unchanged. Zero minus half and half. Thus, what we have obtained is the identity matrix, which is the row echelon matrix, row reduced echelon matrix of the given matrix A, and therefore, the given matrix is invertible, and once you know that it is invertible, the matrix that you have obtained on the right hand side is the inverse of this. So, thus A inverse equal to 2 minus 1 by 2 minus half minus 1 1 0 0 minus half and half. With this we will stop this lecture. In the next lecture we will see some more applications, row elementary operations, especially on solving systems of equations. Thank you all.